Welcome to section 1.4, Predicates and Quantifiers. Math 160, Discrete Methods at Anderson University, South Carolina. Again, we are using the text, Discrete Mathematics and Its Applications by Kenneth H. Rosen. This is Dr. Gilbert Iyabi. Section 1.4, Objectives. Predicates, variables, quantifiers. We shall define these terms. Then we shall look at universal quantifier, existential quantifier. How do we negate quantifiers? And where would De Morgan's laws fit as far as quantifiers are concerned? And we would conclude the section with some translation from English to logic, and maybe from logic back to English. We shall see. Firstly, let us state that propositional logic is not enough. We need something added to it. For example, if we have these two statements, all men are mortal, Socrates is a man, and we ask you if this conclusion is valid or not. Socrates is mortal. How do we represent this as propositional logic? There's a problem. How do we represent all men are mortal? All. How do we do that? Right here, we could say P implies Q. If you are a man, then you are mortal. Socrates is a man, therefore Socrates is mortal. We'll talk about this some more when we deal with inferences. But how do we represent all men are mortal in a generic case? So propositional logic, not enough. We need something else. The following statements cannot be represented in propositional logic. We need a language that talks about objects, their properties, and their relations. And we shall investigate something more about that, even using what is known as inferences. This brings us to what is known as predicate logic, and we shall define a few terms. Predicate logic uses the following new features. Number one, variables. X, Y, Z, omega, and so on and so forth. Lowercase letters would be variables. Next are predicates. If you've done functions, predicates are just functions. Predicates, P of X, M of X, all of these are uppercase letters. Q of X, Y, Z, that means Q is a predicate and the variables that go with the predicate would be X, Y, Z. L could have the variables X, Y, Z, omega. So a predicate could actually have so many variables. The next is quantifiers, which will be covered later, but let's just go ahead and introduce that to you. Quantifiers, there are two of them. You see the symbol? The flipped A means for every or for all. So the flipped AX would mean for all X or for every X. That is known as the universal quantifier. So if you go back to our example, all men are mortal. Now we can represent that statement. For every X, P of X. P of X would mean X is mortal. See that? It's beautiful. And the second quantifier is this E that is looking the opposite direction. It means there exists, or for some X, there exists X. For some X, there exists a man that is mortal. So this is known as existential quantifier, and the first one is known as a universal quantifier. We'll come back to this in a few slides. Propositional functions are a generalization of propositions. P of X instead of P of A. P of A is a particular example. A is just an example from the domain, and I'll explain what a domain is. P of X is the general statement. For example, all men are mortal. That's P of X. X represents any man. P of A, in this case, A is Socrates. That becomes an example, becomes a proposition. Okay, so P of X is a propositional function, and P of A is a proposition. So P of A would have a truth value of either T or F. But P of X is a generalization. It has no particular truth value. Its truth value would depend on the value of X, on what X is. Okay, let's continue. The propositional functions contain variables and a predicate. For example, P of X. X is the variable. P of X is the predicate. Variables can be replaced by elements from their domain. The domain is the set from which variables are taken. For example, for every X P of X, all men are mortal. The set there would be the set of all men. That is our domain. Now I can pick an element from that domain, and Socrates would be an element from the domain. John would be an element from the domain. So variables can be replaced by elements from their domain. Another example, a domain could be the set of integers, in which case 3 is an element in that domain. 5 is an element in that domain. -6 is an element in that domain. So when I define the predicate P of X, I have to watch out carefully where X comes from, what the domain is. Propositional functions, as we have mentioned before, become propositions when the variables, the X, Y, Z, omega, when those variables are replaced by a value from the domain. Example, let P of X denote X is greater than 0, X is positive, and the domain is a set of integers. So P of X is our predicate, X is our quantifier, so P of X is our predicate, and X is our variable. And the statement is X is greater than 0, and the domain is a set of integers. Now, when we replace the variable by a value from the domain, it becomes a proposition, which could either be true or false, but not both. For example, P of -3, that is a proposition, and it is false, because -3 is not greater than 0. P of 0 is false, because 0 is not greater than 0. P of 3 is true, because 3 is greater than 0. As notation, we usually represent the domain with uppercase U. So in this example, uppercase U is the set of integers. Okay? So once more, if I replace the variables in the predicate with values from the domain, those propositional functions become propositions. Then I can do all the things we've mentioned before in sections 1.1, 1.2, and 1.3. And we shall see some of those as we move ahead in this lecture. Further examples. Let x plus y equals z be the propositional function Rxyz. Recall, I told you that a predicate could have more than one variable. In this case, we have 3 variables. And our domain is the set of integers. All 3 variables are from the set of integers. So R2 -15 becomes a proposition. What is the truth value of R215? Ask yourself, would 2 plus -1 equal 5? No, so it's F. R347, would 3 plus 4 equal 7? Yes, so it's a proposition with truth value T. What about Rx3z? Though Y has been replaced here with 3, this is still not a proposition because X and Z are still variables. So that's not good enough. We have to replace all the variables with values in the domain before it can become a proposition, and then we can determine the truth value of that proposition. Now let the predicate or the propositional function Qxyz be x minus y equals z, and you can find out whether Q2 -13, 347, x3z, whether those are propositions or not, and what their truth values would be. Just like the first example, x and z are still variables, and so this is not a proposition. Now let's put sections 1.1, 1.2, 1.3, 1.4 together. That's beautiful. Let P of X be the predicate defined as X greater than 0. Now find the truth values of the following propositions. P of 3 or P of -1. P of 3, 3 greater than 0, that's true. Or P of -1, -1 greater than 0, that's false. T or F is T. So the solution is T. And it could become as complex as you want it to be. You just have to put 1.1, 1.2, 1.3, 1.4 together. Mathematics is not a disconnected piece. It's beautiful. Expressions that have variables are not propositions, and therefore they do not have truth values. P of 3 and P of y doesn't have a truth value because y is a variable. Same thing here, x and y are variables, so these are not propositions. These are just propositional expressions, if you want to coin a complex phrase or a complex statement as that. Okay, when used with quantifiers, though, they become propositions. Interesting. What are these quantifiers that can actually make a predicate become a proposition despite the fact that it still has variables in it? Yes, those two, for every and there exist. That's interesting. Let's look at some of those. the two quantifiers that we're interested in would be the universal quantifier. Remember that symbol? That means for every existential quantifier, there exists. Remember that symbol? So if we say all men are mortal, all would be the universal quantifier. The domain is the set of men. So my predicate becomes X is mortal. So P of X would be X is mortal. So if I write for every X P of X, that would mean for all X in my domain, which is the set of all men, P of X is true. X is mortal. That's my domain. My domain could also be the set of human beings, but I'm interested in men, so I could limit that to the domain that is just the set of men. For every X, P of X. For every X in the domain, the set of men, X is mortal. Now, that would have a truth value. Is it true or false? If it is true, and then I give a second statement, like Socrates is a man, can I then conclude using those two statements that Socrates is mortal? Yes, I can do that. So, all men are mortal. I conclude that is true. I also conclude Socrates is a man, true and true. I can shake my head and say, yes, that means Socrates is mortal. But we shall discuss this some more when we deal with inferences, because that actually is a very beautiful statement. Now, look at the second proposition we have here. Some cats do not have fur. I did say that this beautiful symbol means there exists, or for some. So what this would translate to would be there exists X, P of X. So there exists X from the domain, which is the set of cats, such that X doesn't have fur. How do I know that that statement could be true or not? If I can find just one cat without fur, then some cats do not have fur is true. And while I'm here, let me just talk about negating these things. How do I prove that some cats do not have fur is not true? I have to go through every single cat in the world and prove that none of them would satisfy this condition. For the first one, how do I find a counter example, something to negate all men are mortal? I need just one example. It is called a counter example. If I can find just one person that is not mortal, all men are mortal becomes false. Very interesting. So for every X, P of X asserts P of X is true for every X in the domain, and there exists P of X asserts P of X is true for some X in the domain. The quantifiers are said to bind the variable X in these expressions. So we have for every X, P of X is true. That's exactly what this means. For every X, P of X is true. And this means there exists X for which P of X is true. Again, to prove that this is not true, I have to show that it is false in every single case. To prove that this is not true, I just have to find one example that does not hold, and I'm good. We shall be doing a lot of these when we start section 1.7, proofs, and 1.8, methods of proofs. Okay, let's look at some examples with universal quantifiers. For every X, P of X, we know that it reads, for all X, P of X is true. Or for every X, P of X is true. So if P of X denotes X greater than 0 and U is the set of integers, then for every X, P of X becomes a proposition that could either be true or false. And what would be for every X, P of X? For every X, P of X would mean that for all X in the set of integers, X is greater than 0. If I break that down, that simply means all integers are greater than 0. So for every X, P of X is false. All I need to do is find one example. Negative 3 is less than 0. So for every X, P of X is false. Let's try one more. P of X is the statement X is greater than 0 and U is the universal set and the domain is the set of positive integers. Then for every X, P of X is true. A third example, if P of X denotes X is even and U is the set of integers, that is our domain, for every X, P of X would mean that for all X where X is an integer, X is even. But that's not true because the set of integers is made of even and odd numbers. All I need to do is find one example. 5 is odd. So for every X, P of X is false. Existential quantifier. There exists P of X. or for some x, p of x is true, or p of x is true for some particular x, or there is an x for which p of x is true, or p of x is true for at least one x. The whole idea there is we are just interested in one thing working and we're done. Let's look at a couple of examples. 1. Let p of x denote x is greater than 0 and u is the set of integers. There exists xp of x. When will this be true? If I can find one single integer that is greater than 0. Does it exist? Of course. 5. 5 is greater than 0. So there exists p of x is true. Even if I change the domain to the set of positive integers, it's still true. Now, if I redefine p of x as x less than 0 and u, my domain, is a set of positive integers, there exists xp of x is false because there is no positive integer that is less than 0. Thirdly, if p of x denotes x is even and u is the set of integers, our domain, then there exists xp of x is true because 8 is an even number. All I need to do is find one integer that is even. 10 is 1. Universal quantifiers and existential quantifiers put together with our predicates would cause them to become propositions with truth values T or F. Let's take a quick look at uniqueness quantifier. And the reason why we're looking at this is not because we may use it a lot in 160, but you shall see this again when we get to abstract algebra, advanced calculus, and some of the other more proof-related classes. Let me read this statement for you. This means there exists a unique x such that p of x is true. There is a unique x, very unique, one and only, such that p of x is true. If you put all of this together, it will become a proposition and you can find the truth value of that proposition. Now, there is a unique x such that p of x is true, or there is one and only one x such that p of x is true. For example, let p of x be the predicate x plus 1 equals 0, and let u be the set of integers. Can there be more than one value? Can you have two or more values of x for which x plus 1 equals 0? No, it's unique. There's only one, and its name is -1. Remember the whole talk about additive inverse. There is only one value that can take the number 1 down to 0, and that value is -1. So there exists a unique x such that x plus 1 equals 0 is true, and the unique x is -1. But if p of x is the statement x is greater than 0, there exists xp of x means there is a unique integer that is bigger than 0. That's not true. 1 is bigger than 0, 2 is bigger than 0, 3 is bigger than 0, 4 is bigger than 0, and so on and so forth. So there exists a unique x such that p of x is true is false. It has to be the one and only, nothing else. Now, the uniqueness quantifier is not really needed. We can actually use a different compound proposition to express the idea of there is a unique x such that p of x is true. And this would be that expression. I prefer the uniqueness quantifier. It makes it so easy. There exists a unique x such that p of x is true. Or you can represent all of this with this complex stuff. Okay, let's think a little bit about quantifiers. Thinking about quantifiers. When the domain of discourse is finite, we can think of quantification as looping through the elements of the domain. Say my set A has elements 1, 2, 3, 4, 5. Or the set of students in my Math 160 class. That's a finite set. In that case, to evaluate for every xp of x, you simply loop through all x in the domain. Every student in Math 160 for 2018 is smart. To prove that, I simply go through every student in my Math 160 class, and if they are all smart, then for every xp of x is true. That only happens when the domain is finite. If it is not, then we have to prove it in general, and that gets very exciting. If at a step P of X is false, then for every X, P of X is false. And the reason is because to prove that for every X, P of X is not true, all you need is one example. All the students in Math 160 are males. All I need to do is find one student in the class who is female, and we're done. That statement is false. Now, to evaluate there exists X, P of X, you look through all X in the domain. That is a little different from what we just saw. We had for every X, P of X is true. We go through all the elements and make sure that they all satisfy the property we are interested in. Now, there exists X, P of X. You look through all the elements in the domain, but you really do not have to go through all the elements. If you find even one element that satisfies the property P of X, you stop right there, you're done. All you needed was one element that satisfied P of X. Whereas in the universal quantifier, every single element had to satisfy P of X. Now, you do not conclude that there exists X, P of X is false without going through every single element in the domain and then concluding that it doesn't work. If the loop ends without finding an X for which P of X is true, then and only then can we conclude that there exists X, P of X is false. Now, even if the domains are infinite, we can still think of the quantifiers in this fashion, but the loops will not terminate in some cases. For example, if P of X is the statement X is greater than 0, and I say there exists X, P of X, and X is the set of integers, I can quickly say that is true because I quickly loop in my head through the elements in Z, the set of integers, and I quickly get to 1. 1 is bigger than 0. I'm done. The only thing is I do not terminate because I just keep going. The set of integers is infinite. But once I find one element that does it, that's it. There exists X, P of X becomes true. Okay, let's look at some properties of quantifiers. The truth value of there exists P of X and for every X, P of X depend on both the propositional function P of X and on the domain U. If I change the domain, for every X, P of X could be true or false. There exists X, P of X could be true or false. For example, if U is the set of positive integers, that is a domain, and P of X is the statement X is less than 0, and P of X is the statement X is less than 2, then there exists X, P of X would mean that there is a positive integer that is less than 2. Yes, the number 1. So that statement is true. But if I say for every X, P of X, that means for every element X in the set of positive integers, X must be less than 2. I just pick the number 3. And so for every X, P of X is false. And that all depended on the domain. And of course, the statement, the predicate, the propositional function. Number 2, if U is the negative integers, the set of negative integers, and P of X is the statement X is less than 2, there exists X, P of X would mean that there is a negative integer that is less than 2. That's false. That's true. And for every X, P of X would mean for all negative integers, X is less than 2. That's true. Number 3, if U consists of 3, 4, and 5, a finite set, and P of X is the statement X is greater than 2, there exists P of X would mean there is an element from the set 3, 4, 5 that is greater than 2. Of course, that's true. Pick 3. 3 works. For every X, P of X means all the elements from the set 3, 4, 5 are greater than 2. Yes. So both are true. But if P of X is the statement X is less than 2, then observe that there exists P of X, and for every X, P of X would be false. Again, the truth value of there exists P of X and for every X, P of X depend on both the propositional function P of X and on the domain U. So watch out very carefully for the domain. Don't just look at the propositional function and say, oh, this is obvious. No, the domain matters a lot. Now, let's put sections 1.1, 1.2, 1.3, 1.4 together, we already have the order of operations when it comes to logical operators. Let's add quantifiers in that mix. The quantifiers for every there exists have higher precedence than all the logical operators. So if I give you for every x p of x or q of x, it means for every x p of x, you have to operate this first before you do q of x. As a matter of fact, this or in your brain, you could look at it as plus. Okay, so for every xp of x works first before I add q of x. For every x, p of x or q of x means something different. What this means is, remember parentheses, PEMDAS, for every x, parentheses, p of x or q of x. So I evaluate this first, and for every x holds for p of x or q of x. Now, you may see in some writings that people often write for every x, p of x or q of x to actually mean for every x parentheses p of x or q of x. But you shouldn't follow that example because technically that is not correct. For every and there exists have higher precedence over all logical operators. And if you do this, it's going to be seen as for every xp of x. Then I put the result together with q of x. That brings us to the end of part 1 of section 1.4. And in part 2, we would continue with translation or translating from English to logic. Every student in this class has taken a course in Java. Interesting. How would you translate that? You need a domain, you need a predicate, you need a universal quantifier. We'll get to that in the next lecture. Thank you and God bless you.